All right, we're now taking a look at example 3. So once again, I'm going to make a table of values. I'm going to use my graphing calculator. The reason I'm allowed to use my graphing calculator is because learning target 1 is more about evaluating functions. And so because you're demonstrating knowledge of the evaluating functions in that learning target, I'm going to enable myself to use my graphing calculator's table. Okay? So for this function, once again, I can't factor him, which is why I'm not using that strategy from the first example. And I'm going to plug in values between -3 and +3. Okay? And at -3, I have a y value of -49. -2, I want -15. -1, I'm at 1. 0, I'm at 5. 1, I'm at 3. 2, I'm at 1. And 5, I'm at, or 3, I'm at 5. Okay? So a few observations that your textbook points out. Notice that when we go from a negative to a positive, that means I have to cross over the x-axis, which means that I have a 0 that exists between -2 and -1. Something else that you can make an observation of. Notice that when I go from 1 to 5 to 3, I jump up from 1 to 5 and then jump back down to 3. This means I'm starting at 1, going up to 5 and back down to 3. It creates a relative maximum. Okay? I like to kind of think of them as camel humps, the top of a camel hump. Okay? So then once again, let's look at the opposite. We go from 3 down to 1, but then back up to 5. So here was 3, we went down to 1, and then shot back up to 5. This little location is called a relative minimum. Okay? Now, not always will you have nice relative extrema. Okay? That's where you will need to have your graphing calculator find the precise points. And once again, we will talk about that calculator in class. Okay? All right, so let's plot these points. Once again, I'm noticing that I kind of have some larger numbers on the larger sides. So let's actually go in increments of 5 again. So 5, 10, 15, 20, 25, 30, 35. So I'm still going to be off the paper here. So at -3, I'm all the way down. We'll approximate right here with -49. At -2, I'm going to be at -15. -1, I'm about right there. 0, I'm up at 5. 1, I'm down at 3. 2, I'm down at 1. And then back to 3, I'm at 5. Okay? And so once again, because I have a third-degree polynomial, it's an odd degree, and a leading coefficient is positive, it's going to create this general shape for a cubic function. So now, I'm just going to connect my dots. Notice that I got some curve. Now, it's probably not the best graph I've ever drawn, but it shows precision with my xy table. And notice we have those points we discussed, where we have a relative minimum located at 2, 1, and then we have a relative maximum located at 0, 5. Okay? Once again, we can also make the observation that our domain and range is all real numbers in this scenario because it's an odd degree polynomial. All right, so we're now taking a look at our very last example, and it's modeling a real-world situation that's discussing the average fuel consumed by individual vehicles in the U.S. starting from 1960 going to 2000, okay? All right, so we're going to make an XY table again, but I'm actually going to start at 0. And 0 is going to represent the year of 1960, okay, my starting spot, okay? And at 0, if I plug that in, I'm going to get 654. Okay, so what that represents in the context of this problem is the amount of gallons, 654 gallons, was consumed by an individual vehicle in the United States. Okay? Now that's a large number, and so that's where I'm definitely going to have to adjust the scale on my graph. Okay? So if we go up by 5s, okay, 5, 10, 15, 20, 25, 30, okay? Actually, we've got to go up to 40 to get up to 2,000, okay? 35 and 40, okay? 40 years from 1960, that gets me 2,000, okay? That's also following what your textbook says. Once again, I have my graphic calculator. I'm typing these all in and finding that 5 years from 1960, we have 710.88 gallons. 10 years from 1960, so 1970, we have 711.5, okay? Making an observation, notice that we went from 654 to 710 to 711, and then dropped down to 674.63, okay? This is indicating that it's almost going to look like a little bit of a camel hump here again, pointing out that relative maxima location here. Okay? Well, if we have an x value of 20, we're going to have a y value of 619. At x value of 25, we're at 563.38. X value of 30, we're at 526.5. Let's scroll down on the table. 35, we're going to have 527.13. So then once again, notice we dropped from 563 to 526 and then back up to 527. So that's going to create this other shape where we're going to have a relative minima located. And then at 40, we're going to have 584, and we're going to just continue to start to increase, which you could see if you continue to plug in bigger values for x. But in our scenario, our x-axis is going to represent time, okay? And then our y-axis, which we're going to just call a function of t, okay? That's representing the number of gallons on average consumed by this individual vehicle, okay? So in your textbook, what it does is a little bit of a zigzag. That means that we're just going to skip ahead a little bit to a few larger points, okay? So notice that our lowest value that I'm seeing in my XY table is a low value of 526, okay? I'm actually going to start this graph at 500, okay? That way I can recognize I do get a little bit low. Low is 526, but I'm going to be more precise with 500, okay? And then let's go up. And I got to get to a large value of about 711, at least on my graph. So I want to get up to a total of about 750, okay? So if we go in increments of 50, 550, we're going to do 600, we'll do 650. And notice that I just chose to completely ignore the axes provided, which you can always feel free to do as long as you're clearly labeling. All right, so then once again, we can also just relabel our x-axis or our axis for t here. We can do 10, 20, 30, 40, or it could have even gone bigger, okay? In fact, why don't we ignore that? Let's go every 3 boxes represents 10. Okay. A little bit hard to do with our 5s, but that's okay. So 10, 20, 30, and 40. Okay. So at 0, we have a starting value of 654, so approximately right here. Let's jump to 10. 10, we're at 711, so approximately right here. At 20, we're at 619, so approximately here. At 30, I'm at 526, so just above that mark. And at 40, I'm at 584. So why did I skip all those other middle ones? Just because they were a little bit harder to do. I will do them now. So at 5, which is going to be halfway between 0 and 10, I have an y value of 710, so approximately right here. Okay? I want you to make an observation. Halfway between 5 and 10, because they're not symmetrical, there's going to be something slightly bigger than that. Okay? We're not necessarily certain that this spot here at 10 is going to be our exact maximum. There's going to be something slightly larger because they're pretty close, but obviously it had to hit a point and come back down. Okay? That's when you're going to use your calculator. Halfway between 10 and 20 is 15, and it had a y value of 674, so approximately right here. All right, then between 20 and 30 is 25, and that was at 563, so approximately here. Halfway between 30 and 40 is 35, and we're at 527, so right about here. Okay. So now I'm going to create the shape to my cubic function. Curving it. And shoot up. Okay, so then parts B and part C are just about analyzing the function. So part B, when it's asking for turning points, it's just asking me to look at my relative max and min. So specifically, we're noticing that a maximum is occurring right between here, between the 5 and 10 year mark. Once again, we can go into the calculator and find a more specific spot. So that means that we have a maximum amount of fuel consumption by an individual vehicle. And then right around here, between 30 and 35, we're going to hit a minimum, where we're having a minimum amount of fuel consumed by any individual here. Okay? And then all of a sudden, we're going to start to increase, okay? We're rising, rising, rising up, okay? So end behavior, something that we can say, we don't need to look at the left-hand side. We're only looking as t is getting larger. As we're going to the right, so we're approaching positive infinity. And as I'm going to the right, notice that my function is going up, 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 up. That means he is also going to be approaching positive infinity. Okay? You can also notice that just by analyzing the leading coefficient and the degree of your polynomial. Okay? All right, so specifically in part C, what trends in fuel consumption does the graph suggest? Okay? So around this range here, so around 30 years from 1960, so about 1990. At the start of 1990, we just start to see it increase by the amount of fuels. Now, amount of fuel in gallons consumed by an individual. Do I see this being realistic, modeled by a cubic function? Not necessarily, but the graph will suggest that we are increasing pretty quickly the amount of fuel consumed.